Welcome back to this channel. In this video, I am going to talk about electric field. Now, before you watch this video, if you have not seen any video on electric field at all, you should go back and see my other videos on electric field in order to understand this concept in detail, because in this video, all I'll be doing is calculating, showing you calculation, because students often find it difficult to understand the vectorial analysis for electric fields. Okay, so I'm going to be showing you that in this video. So if you don't understand anything on the electric field at all first, I'll link those videos in the description where I've talked about electric fields. Do well to see them. All right, you should already know, I assume, that the electric field is the region in space around an atom, around a charge, where the force due to that charge can be felt. The region in space around a particular charge, so let's say there is a charge here, the region around it where the force due to this charge can be felt is the electric field of this charge. Make sense? Good. So a question can now come in this form, saying that you should find the electric field due to now this is electric field due to multiple charges. Okay, multiple charges. So when there are multiple charges in a particular location, so for example, let's say there's a charge acting along this x-axis. I'm going to use the simple ones first, okay? So let's say there's a charge acting along this axis. There's a charge placed here. Let's say this is the point we want to consider. Let's say point P. So calculate the electric field intensity at point P, for example. So let's call this our point P. We want to calculate the electric field intensity at that point P. At point P, electric field at point P due to, let's use three charges first. For example, let's use three charges. So let's say there's a charge that's acting along this axis. There's a charge, let's call this charge 2 microcoulomb. Let's have another minus 5 microcoulomb acting around here. And let's have another, maybe let's just say 6 microcoulomb acting along here. Alright? So, and the distances are, let's say, like 2 centimeters here, 3 centimeters here. Let's say this one looks like the longest, let's just say 5 centimeters. We're asked to calculate the electric field that will be felt by the electric field intensity that will be felt by a unit charge placed at this position P. How do you solve that? How do you solve that? Now, very simply, what you do is you first calculate the electric field intensities due to each of these charges. Okay? Now look at it. If the electric field intensity was just due to one charge, then you can know what the electric field will be here. But all of these guys have their electric fields. They are interfering at this point. So what will be felt? What will be intensity that will be felt at this point? Exactly, that's what we want to calculate. So let us start from this guy. So let's call this guy E1. Let's call this guy electric field intensity 2, E2. This will be like E3, okay, due to charge 3. So now recall that the formula for electric field intensity, I'm just going to do a little bit of derivation again so that you remember that E is F over Q, right? Do you remember? Force per unit of charge placed at the point. So that means that E will be equal to F is K Q1 Q2 over R squared. So times 1 over Q. Q takes care of Q, and then our formula becomes KQ over R squared. Makes sense? So if this makes sense, then we can therefore say that for E1, electric field intensity due to charge 1, that is E1. That will be KQ, our K. Recall that our K is 9 times 10 raised to the power 9. That is already given. Or 1 over 4 pi epsilon naught. That's what should be. But we are usually given this in our exam. But if you are not given, you will know that you will use K is the same as 1 over 4 pi epsilon naught. I'm just trying to make sure that I'm touching on all the details you need. With epsilon naught being equal to 8.87 times 10 raised to the power minus 12. So just find your way around it. Epsilon naught is permittivity of free space. In a case where you are not giving permittivity of, let's say you are giving another medium, the permittivity of that medium will be equal to the permittivity of free space times relative permittivity. If you're giving relative permittivity, you know permittivity of free space will be this. So it means that your K therefore becomes 1 over 4 pi E epsilon naught will now become EM over ER. EM over ER, that is ER over EM. So this is the formula for if you are not giving permittivity, if you are giving a different medium that is not free space. But for this case, we are using this. This is our general constant that we normally use, okay? This 9 times 10 to the power 9, it has a unit, but let's not bother about those things here. I just want to show you how to solve by vector, okay? Now, E1 is 6. It will be K, which is K times Q. K is 9 times 10 to the power 9 times Q1, which is 6. Now, mu farad, our Q1 is 6 mu coulomb rather. Mu coulomb is microcoulomb, that is 6 times 10 to the power minus 6. This micro means times 10 to the power minus 6, good. So this now becomes 9, which is our constant, times charge, which is 6 times 10 to the power minus 6, all over r squared. The distance between that point and that charge is 3 centimeters. Our r in this case is 3 centimeters. Now you convert to meters, this becomes 0.03 meters. Now you will square it. Makes sense? Since you will square it, I can just square this here. This is already 3 times 10 to the power minus 2. By the time you square that, what does it become? R squared becomes 9 times 10 to the power 4. So in power minus 4, sorry. So in other cases, what I'll just do is I'll give you the R squared directly here. Is that clear? So R squared here is that guy, which is 9 times 10 to the power minus 4. This takes care of this. And E1 becomes 6, that is left alone here, times 10 to the power 9, then times 10 to the power minus 6, divided by 10 to the power minus 4. I hope you understand this. Divided by this one has gone. So our E1 becomes 6 times 10 to the power 9. Multiplication of base means subtraction of power. Addition of power, that is plus minus 6, that's minus 6. Make sense? Multiplication of base means addition of powers, you will add this power. But division of base means subtraction of power, that's minus 4. I hope that is clear. So this becomes 6 times 10 to the power 9 minus 6 plus 4. By the time you solve that, this plus this is 13. 13 minus 6 becomes 6 times 10 to the power 7. Newton per coulomb, that's the unit. Newton per coulomb. Okay, that's E1. Now what will E2 be? E2 is the charge, electric field intensity due to this charge minus 5 coulomb. So our charge Q here in this case, so for E2, our Q is minus 5 microcoulomb, which is 5 times 10 to the power minus 6, okay? And the distance R is what? 2 centimeters. So R squared is what? 4 times 10 to the power minus 4. I hope you understand. You convert this first. After converting it, it will be 0.2 times 10 to the power minus 2 in meters. So this will now be, by the time you square it, it gives you this in meters. So I can just plug into my equation. E2 becomes K, which is 9 times 10 to the power 9, then times Q, which is 5 times 10 to the power minus 6, divided by 4 by 10 to the power minus 4. Make sense? So you now have 9 times 5 is going to give you 45. 45 divided by 4 gives you 11.1 over 4. That gives you 11.25. Okay? 11.25 times 10 to the power. I just solve the whole numbers together. Okay? This times this divided by this. Then I bring this one separately. The same way, times 10 to the power 9 times 10 to the power minus 11 divided by 10 to the power minus 4. The same sequence repeats itself. So we'll just say 9 minus 6 plus 4. It gives us this again. That is 11.25 times 10 to the power minus 10 to the power 7 Newton per coulomb. Now you see that I'm not converting to standard form yet. I did not say it is 1.1 times 10 to the power 8. I want to first leave it this way because of they look the same, they look similar. Okay, so I want to leave it that way. Now let's go to E3, that is electric field due to charge 3. You know that Q3 in this case is going to be 2 microcoulomb. No, we did 5 just now. So this will be, now notice that the negative did not affect, but the negative will have an impact. So just wait. It has a negative here, so it will have an impact. That's what students normally confuse, and that's what I want to show you here. So E3 will now be equal to Q3, which is 2 times 10 to the power minus 6. Okay, so E3 therefore becomes K, which is 9 times 10 to the power 9, times Q, which is 2 times 10 to the power minus 6, divided by R squared. What's the distance here? The distance is 5 centimeters. Now 5 centimeters will give us 25 squared. When you square it, right, times 10 to the power minus 4. Is it clear? By the time you take R squared, is it clear now? When you convert and square it. Alright. So 9 times 2 is 18. 18 divided by 25. Let's use our calculator here. 18 divided by 25. This gives us 0.72. So we have E3 becomes 0.72 times 10 to the power 9. The same sequence repeats itself, plus 4. So we have 0.72 times 10 to the power 7. Now you can decide to leave it this way if you want to, for the purpose of making your work easy, because they have the same powers, 10, 10, 10, 10. 10 to the power 7, 10 to the power 7, 10 to the power 7. Exactly. You will soon understand now. Now, in order to know the actual electric field intensity that will be felt here, these that we just calculate, these guys are the intensities due to each of the charges individually. But what intensity will be felt here? That's what we want to calculate. Now we'll now do the vector sum of both of those. Now when we want to do vector sum, you know what we have to do is resolve in vertical, in x component and what? Y component. Does that make sense? Why? Because that is the summary of their action at this point. The x component and the y component. Makes sense? So now we are going to do, remember that because what we are trying to do is the resultant intensity that is at this point. Exactly. So if it's the resultant intensity, remember that when we take the y component and the x component, the resultant will be, using triangular law of vectors, the resultant will be this, right? The resultant will be this. So if this is the resultant, then this becomes the hypotenuse, this becomes the opposite, this becomes the adjacent. So hypotenuse squared equals opposite squared plus adjacent squared. So that's where the formula that I want to write now, that's where it came from. So the resultant of those forces will be equal to the square root of, you know, our resultant I said is our hypotenuse squared, right? Will be equal to opposite squared plus adjacent squared. So our hypotenuse will be square root of everything. So the same way, it will be square root of the sum of electric fields on x-axis all squared plus the sum of summation electric fields on y-axis all squared. Is that clear? So if this be the case, then let's first find the sum of electric fields on x-axis. What are the electric fields that are on x-axis? This guy is on x-axis, this guy is on x-axis. This guy is on x-axis. Now here is what you should really take note of now. Listen carefully. This guy is a positive charge, right? For a positive charge, how does the electric field go? It goes radially outward, right? Radially outward. So it means that relative to this part, the electric field will be going in this direction. Electric field will be going in which direction? This direction. And what direction is this? In your Cartesian coordinate system, you have x, positive x, positive y, negative y, right? So if you are going in this direction, where are you going? You are going positive x. You are going positive x. So it means that the electric field due to this one, which is E1, will be positive. Is that clear? So E1 is positive. So we say sum of the ones on x-axis will be 6 times 10 to the power 7 plus, let's check the other guy. E3 is also, oh, that's what I was supposed to write first. I'm sorry. The guys on x-axis are E1 and E3. But now we know E1 is in positive direction, which is 6 times 10 to the power 7. Now, for those that don't understand, if this were to be a negative charge, the electric field will be going radially inward, which means electric field will be going in this direction towards 6. So if electric field is going towards 6, which direction is that? Negative x. So that will be minus 6 times 10 to the power 7. Is that clear? Alright. So then plus E3. Sorry, I said E1 and E3 are the ones on the x-axis. For E3 is this. Now let's see, for a positive charge, it's also positive, right? It's always going radially outward. Now outward from this guy will be in this direction, right? So it means it's going in that direction, which is which direction? Negative direction. So it becomes plus minus, what's the value? 0.72 times 10 to the 7. So this becomes 6 times 10 to the power 7 minus plus times minus. Minus 0.72 times 10 to the power 7. Now, times 10 to the power 7 is common, right? So we have 6 minus 0.72, both of them times 10 to the power 7. Do you now see why we did not change this now? We did not convert this to standard form yet. All right. So by the time you subtract this, you are going to have 0.28. That will be 5.28. 5.28 times 10 to the power 7 Newton per coulomb. So this is the summation of electric fields on x-axis. Now let's find the electric fields on y-axis. Electric fields on y-axis. The sum of electric fields on y-axis will be equal to, how many electric fields do we have on y-axis? This guy alone, okay? This guy alone, only E2, is only E2, okay? But will it be positive or negative? Let's see. Now, for this guy, is a negative charge. So electric field for a negative charge is going radially inward. So it means it will be going inward into that charge, right? It's going in direction of that charge. And this direction is what? Positive y. Positive y. So it means it will be positive. So E2 will be positive. So that will be 11.25 by 10 to the 7. All right. Newton per coulomb. So we can now say that our resultant electric field, the electric field will be equal to the square root, let's call it like R sub E. Okay? No. Electric field resultant, let's say E sub R. Make sense? Will be equal to the summation of electric field on x-axis, which is 5.28 times 10 to the power 7 squared plus electric field on y-axis. Where is that? This 11.25 times 10 to the 7 times 10 to the 7, sorry, all squared. This becomes the square root of this squared. Let's square that. 5.28 times 5.28. Is equal to 27. 27.87, that's like 88. 27.88, approximately this. Then square, if you square this guy, see, 10 raised to the power 7 squared is equal to 10 raised to the power 14, 7 times 2. Is that clear? Okay. So this times 10 raised to the power 14 plus 11.25 times 11.25. 126.56, then still times 10 to the power 14. So times 10 to the power 14 is common, so we have this plus this plus 27, so we have 27.88 plus 126.56. Both of them times 10 to the power 14 is common between them, right? Plus 27.88. It gives us 154. So we have the square root of 154.44 times 10 raised to the power 14. So what this becomes is the square root of this 154.44 times the square root of 10 raised to the power 14 is the same as 10 raised to the power 14 times half, because the square root of 9 is equal to 9 raised to the power half. Makes sense? So I can say the square root of 10 raised to the power 14 is 10 raised to the power 14 times half. So that's why I'm bringing it out as 10 raised to the power 14 times half. So this half takes care of this. It gives us 7. Then the square root of this square root, where is square root here now? The square root is, sorry, the square root of 154.44 is equal to 154.44. This calculator is having issues. I think it's 12.42 or something. 12.443 times 10 raised to the power 7. So this is the answer. This is the electric field, so Newton per coulomb. This is the electric field intensity that will be felt at point P. Is that clear? That's the electric field intensity that will be felt at point P. Now, what if the question now goes further to saying that you should calculate the force, on a 3 microcoulomb placed at P. So let's say a 3 microcoulomb is placed at point P. What will be the force on it? Remember that the force, formula for force, is the same as E times Q, electric intensity times Q. Because you remember that that's how we derived it. Okay? So F therefore becomes, what's the electric field intensity at that point? Is this 12.43 times 10 to the power 7 times the charge. This 3 microcoulomb, that will be 3 times 10 to the power minus 6. So force therefore becomes, this one is Newton per coulomb. This one is coulomb. Coulomb cancel coulomb. So our answer will end up being Newton, right? So we have 12.43. 12.43 times 3. That is 36.9. So the answer is 36.9. 36.9 times 10 to the power 7 minus 6. That will be 1, right? That's 7 plus minus 6. So F becomes 36.9 times 10 to the power 1. By the time you convert to standard form, it becomes 3.69 times 10 to the power 2 Newton, or 369 Newton. Is it clear? So that's the answer for a force, or the force that will be felt by a 3 microcoulomb that is placed at that point P. Let me solve just one more question, and you'll see by that time you should be able to get a better grasp of this thing, this concept. So now write this new question that says calculate the electric field intensity at point P due to 4 charges now. Let's not deal with 4 charges. Don't worry, this time I'll be faster, but make sure that you are following. Make sure you are following. I will explain the same way, but I'll be a little bit faster. So due to 4 charges now. Four charges. What are the 4 charges? Let's say there's a point P here. Let's call this point P. There's a charge minus 3 micro. Now let's put 3 microcoulomb here. Let's put 6 microcoulomb here. It can act at an angle, okay? So we have 6 microcoulomb. Let's say 4 microcoulomb here, okay? And 5 microcoulomb here. The distance between these two, let's say 2 centimeters, the distance here, 3 centimeters, the distance here, 4 centimeters, the distance here, 3 centimeters. Now watch, to solve this one, to find the intensity at point P is simple, okay? Simply calculate the electric field intensity due to all these charges. So let's put minus here. Let's say there was minus charge here. Let's add a minus charge. Maybe we should even put minus here. Exactly. So if we put minus here, minus here. Let's take it from here the same way. E1, E2, E3, E4. So E1 will be equal to KQ1 over R squared over this distance. That will be K, which is 9 times 10 to the power 9 times Q, which is 5 times 10 to the power minus 6 micro. Take note, make sure it is micro before you use 10 to the power minus 6. All over, the distance is this, so now square that, convert to meter and square it, gives 4 times 10 to the power minus 4. By the time you do this, I think we did something like this before. It gave us this times this 11.25. That's what it gave us. 11.25 times 10 to the power 9 minus 6. Now let's change it. I don't want it to give us something. Okay, it's the same. It's the same. Raised to the power 7 because it's the same sequence. Do you understand now? Newton per coulomb. Just use your calculator, you see you get this, okay? You get it. For those that are contemplating how did I get whatever I got. So for E2, that will be this guy, 3 microcoulomb, 3 times, that will be 9 our charge. Recall that this is the formula we're using, equal to KQ over R squared. K is 9 times 10 to the power 9 times Q, in this case is 3, times 10 to the power minus 6 micro over the distance is 9 and 3 centimeters. That will be 9 times 10 to the power minus 4 meters. This takes care of this, and then we have equal to 3 times 10 to the power 9 minus 6, 3 plus 4, 7 again, Newton per coulomb. Is that clear? Then someone is asking now that will it always be as sweet as this, that it will give us 7 all the time? I'm not saying so. All right. Now for E3, which is this guy, that becomes K, which is 9 times 10 to the power 9 times Q, which is 6 times 10 to the power minus 6 over, what's the distance between them? 4 centimeters. That will be 16 times 10 to the power minus 4 by meters. By the time you convert that 4 centimeters to meters and you square it, is what you will have. Here 1, here 3, here 8. So 9 times 3, 27 divided by 8. That becomes 3.27 divided by 8. 3.375. So we have 3.375 times 10 raised to the power 7 again. Is that clear? Alright. Newton per coulomb. Then E4 will be the fourth charge here. That will be 9 times 10 to the power 9 times 4 times 10 to the power minus 6 over the distance, 3 centimeters. That's 9 times 10 to the power minus 4 again. This takes care of them. We have 4 times 10 to the power 7 Newton per coulomb. So these are the electric field intensities. Now let's now do the vector sum. So we have to first know the summation of the electric fields on x-axis, and then we'll do summation of electric fields on y-axis. So the summation of electric fields on x-axis, which ones are on x-axis? These two, E1 and E3, right? E1 and E3. Now E1 is negative. Where will be the direction of the field? Towards it. Which direction is this? Negative x or positive x? This is negative x. So it will be negative. E1 is negative. So this answer here is negative. So that will be minus 11.25 plus E3 is positive. Which direction will positive push? Positive charge is radially outward, right? It will be away from this charge. So it will still be pushing towards the direction. So what direction is that? Negative again. That becomes plus minus E3, which is this, 3.375. So we have 3.375. Clear? Both of them times 10 raised to the power 7. They both have 10 raised to the power 7, right? So we just factorize. So this becomes minus this. So that's just you plus it up, right? You add it up, right? So you have 14.625 times 10 raised to the power 7. Newton per coulomb. So this is E on x-axis. Now summation of E's electric field on y-axis are just these two guys, right? Okay. Now if they are just these two guys, electric field due to these 3 microcoulombs. Stick with me till the end though. The last one I'll solve now is the one that has an angle. Okay? So the electric field due to this guy is going to be radially outward because it's positive. Outward in this direction will be where? Down, right? Outward because it will be away from the charge because it's positive. Electric field goes out away from the charge. So away from the charge here is down. What direction is down? Negative. So this E2, some of these guys on the y-axis are E2 and E4. They are the only ones on y-axis. So for E2 now, that will be negative because we said to push out. That will be minus 3 times 10 to the power 7. Okay, plus the other guy, minus 4. Minus 4 for a negative charge, it is always radially inward, that is towards the charge. Where is this charge? It's down, and towards it is also down. That's also negative again. Yes, sir. So that becomes, sorry, this will be minus, so please. Minus this is minus 14. So minus the last one, that will be minus 4 times 10 to the power 7. Since they have the same distance, that becomes minus 3 minus 4, all times 10 to the power 7. Minus 7 times 10 to the power 7 Newton per coulomb. Is this clear? If that be the case, then the resultant electric field becomes the square root of electric field on x-axis all squared plus sum of electric fields on y-axis all squared. But what we have eventually will be sum of electric field on x-axis will be minus 14.625 all squared plus, times 10 raised to the power that thing in place. But of course, if you notice, that by the time let's just put it so that some people will not get confused, okay? Let's put it times 10 to the power 7 all squared plus this guy, negative 7 times 10 to the power 7 all squared. By the time you square 14.625 times 14.625. So someone is asking now that, will it become minus? Now when you square a negative number or a positive number, you will get a positive number. Is that clear? So someone is now asking that, why should is it compulsory to put the minus? Yes, if you are solving, you are doing a written exam, yes. So we have 213.89, that's the square of this, times 10 to the power 7 squared becomes 14. If you square this one, it gives you 10 to the power 14. So the square root of all of this plus 7 squared is 49 times 10 to the power 7. Makes sense? 10 to the power 14. So by the time what we have is E sub r becomes the square root of this one plus this one. That is 213.89 plus 49 becomes 262.89 times 10 to the power 14. By the time you take square root of this one, it becomes square root of 262.89 times square root of 10 to the power 14, that is 10 to the power 14 raised to the power half, right? You see it cancels out. So next time, we can just leave the 7 out because it will come back to 7. Makes sense? So the square root of this is 16.214 times 10 to the power 7 Newton per coulomb. So do you see that now? So that is how to find electric field intensities due to multiple charges. Now, what if we now have the ones that are acting at an angle? So, for example, in some cases, you'll be given the angle, other times you might need to find an angle, depending on what's the modality of the question. You know what? I'll just show you what to do, okay? I'll show you what to do. But the process is pretty much alike. It's pretty much the same thing. Let's say I ask you to find the electric field intensity at point P here, due to 3 charges. Let's say there's a charge here, there's another charge here, 4 microcoulomb, there's another charge here, 5 microcoulomb. Okay, now look at this one now. Let's say we now put another charge here, 4 microcoulomb. Let's say 6 microcoulomb, for example. Let's say negative 6 microcoulomb. Now you have to draw the line. You'll be given an angle that this here is 30 granules, for example, and you'll be told that here, this one is at about maybe let's even say 40 granules. How do you find the electric field at this point? How do you find the electric field at this point? You draw your Cartesians, just calculate the distance, measure the distance here, measure the distance here. Now, if you are given the distance here, and you are given the distance here, for example, let's say you are giving here as 2 centimeters, here as, let's call it like 4 centimeters, here, let's call it as like maybe 3 centimeters. How do you find the distance between this point that we are calculating electric intensity at and this one? You just use your Cartesian coordinate system and your right angle geometry. So this place becomes 4 centimeters, this place 3 centimeters, this becomes the hypotenuse. So what do you say? Hypotenuse square is equal to opposite square plus adjacent square. Hypotenuse square therefore becomes the square root of opposite in this case. Opposite in this case is going to be here because of our angle is here. Our angle is here. Opposite is 3 squared plus adjacent is 4 centimeters. 4 squared. So this becomes square root of 3 squared 9 plus square root of square of 3 9 square of 4 16. 9 plus 16 is 25. So by the time you do the square root of this, wow, it gave us a fine number. So this will be what? 5 centimeters. So here you could be giving the distance away from here, and you may not be giving as well. You could be giving maybe this one. They could tell you that this 5 microcoulomb is equidistant away from a 4 microcoulomb and a 5 microcoulomb on opposite side of the plane. So it means that this place will also be about 3 centimeters. I don't want us to use that. Let's say this place was actually 5 centimeters. You do the same thing that I just did now to calculate this place. Is that clear? Good. The next thing you now do is this. Calculate. Okay, let's do it. That becomes 4 squared. This place becomes h equals 4 squared plus 5 squared. That's 25 plus 16. Square root of that, we have square root of this plus this. That's 41. Square root of 41. Right. So this place is square root of 41 centimeters. That's the unit. Okay? You can convert that to, let's solve that really. Where's the calculator? So by the time you solve this, square root of 41 is 6.40. So that will be 6.40 centimeters. Alright. So now if you know how to calculate electric field intensity, you can choose this as your E1, E2, E3, E4. And calculate how many charges you have. 1, 2, 3, 4. 4 charges. If you want to do this, E1 will be equal to KQ1 over R squared. That will be 3 over, please stick with me. That will be 9 times 10 to the power 9 times 3 times 10 to the power minus 6. Over what's the distance? 3 squared. 3 centimeters. You convert and square. That becomes 9 times 10 to the power minus 4. You have been getting that since you understand what I just did. This is 3 raised to the power 7 Newton per coulomb. Now what will E2 be? E2 is acting along this distance. Does that make sense now? This is the line of separation. Do you understand now? So this is the distance you will use. Take note. So E2 becomes 9 times K, which is 9 times 10 to the power 9, times Q, which is 4 times 10 to the power minus 6, over this guy squared will give you 41, if you remember, because you took square root of 41. So 41 times 10 to the power, if you convert, minus 4. Is that clear? Good. By the time you solve this, you get an answer. E2 becomes 36 over 9 times 4, 36. So 36 divided by 41. That gives you 0.878 times 10 to the power 7, pretty much 7 Newton per coulomb. Seeing that everything is giving us 7 so far, then let's not convert yet. Let's not convert. Then for the next guy, and this guy, you calculate, this will be your distance. For the next guy, you calculate this will be your distance. Let's do it. E3 will be equal to 9 times 10 to the power 9 times this one, which is 5 times 10 raised to the power minus 6. This is the distance we are using, not this. Okay, this one is distance between the two charges, not the point we are calculating intensity for. So 4 squared, 16 times 10 raised to the power minus 4 is squared, but after converting to meter. Make sure you are converting to meter. Okay, for those that have forgotten, let me quickly tell you what I am doing. That 4 centimeter is equal to 0.04 meters. So that is 4 times 10 raised to the power minus 2. By the time you square, because the formula is kq over r squared, by the time you square it, becomes 16 times 10 raised to the power squared is minus 4. So that's what I'm doing here. Okay? So 9 times 5 is 45. 45 divided by 16. That will give you 2.81. That will be 2.81 times 10 raised to the power pretty much 7 again, Newton per coulomb. How about E4? Now E4 is what? E4 is the resolution that is the problem. So make sure you follow until the end, please. Please, I am begging you. Follow to the end, please. You know, there are some students that even when you beg them, they will not listen. Do you understand? But if you want to know it, please stay till the end, okay? I mean, if you want to know it, just stay till the end. What is E4? That's this guy. 9 by 10 raised to the power 9 times 6 times 10 raised to the power minus 6 over r squared. What's the distance of separation? 5. So that gives you 25 times 10 raised to the power minus 4. 9 times 6, 30. 9 times 6, 54, right? 54 divided by 25. That gives you 2 point something again. Divided by 25. That gives you 2.16. 2.16 times 10 raised to the power 7 again, Newton per coulomb. Now, here comes the real work. So you now have to bring all the guys by vector resolution now. The summation of forces on E, summation of electric field on x-axis will be, E1 is not on the x-axis at all, it's on y-axis, C. But E2 can be resolved to x and y-axis, so we can have E2 plus E3 is already on x-axis, it's not on y-axis at all. E4 can also be resolved E3. E4 can also be resolved to y-axis. Now, what is E2? E2 will be E2, the value of E2, to resolve it to x-axis. You will be, you know, there's an angle here. Angle is 40 degrees. You'll be opening the angle. That will be, and if you are opening, just remember, when you open an angle, I've proven this time without number, so I don't want to prove again, okay? Close. When you open an angle, use sine theta. When you close an angle, use cos theta. So that will be, we are opening this angle, that will be sine 40. Or you are closing, which angle will be here? 50. So sine 40 will be equal to cos 50. Does that make sense now? So E2, which is this value here, 0.87 times 10 to the power 7 times, we are resolving it to y-axis. That will be, when we are opening 40. So that will be sine 40 times sine 40 plus E3 is already on x-axis, so we use it directly. Where is it? 2.81 times 10 to the power 7. Then plus, sorry, there's something I also should point out. Let's start again. This E2 is here. Now this E2, if you resolve it here, is it pushing in this direction or in this direction? So you see, you have to be careful. If you resolve it here, is this guy pushing or is it pushing or towards itself? It is pushing away. And what direction is this? Negative, please. So this has to be what? Minus. So you see why you have to be careful now. And that's why I said you should stay till the end. See, I almost made a mistake because I was rushing. Look at now, the next one is a positive guy again. This guy is also, for a positive charge, electric field is also radially outward. So it will be pushing away in this direction, negative again. So this is supposed to be minus. Plus times minus is minus. Is that clear? Good. Then for 6 microcoulomb, we can resolve it to y and resolve it to x. It has 2 components. So since we are doing for x components, let's resolve it to x first. By resolving it to x, we are closing 6 closing 30 degrees. But this angle is too big to be 30. But let's use it because I didn't draw to scale at all. So 30 degrees, you are closing 30 degrees. That means it's cos theta. But first let's analyze it. What direction is that? If you resolve it to this point, to this direction, will it be, because the negative charge, will it be towards it or away from it? For a negative charge, electric field is always radially inward, right? So inward, that will be in this direction. Inward will be this direction, that's positive. So plus the E4 guy, that's 2.16 times 10 to the power 7 cos 30, because we are resolving it by closing that angle. Is it clear? Now, let's do for that of the sum of electric fields on y-axis. So you do this one, you write the answer, then you know how to go about finding the resultant by yourself. Let's do for y-axis too. The y-axis, guys, we have E1 is on y-axis, not on x-axis at all. For E2, it has y component, so E2 for y component. Then the guys on E3 is not on y-axis at all. E4 has y component, so we have E1, E2, E4. So E1 is perfectly on y-axis, so we just write the answer. E1, that's 3. Now let's check again. Check. Will it be positive or negative? It's radially outward. That is negative. That is pushing away towards negative y. So that will be negative. So you see, you have to be very careful. That will be minus E, which is 3 times 10 to the power 7. Plus, what is E2? E2 here is positive. By the time you resolve it here, you'll be closing 40, right? So that will be where is E2? 0.87 times 10 to the power 7. Now you are closing 40, that is cos 40. But check, will it be positive or negative? Positive or negative? Is the positive charge is radially outward. Outward means away from the charge. Now be pushing that guy towards where? Negative y. So this becomes minus. Is it clear? Then plus E4 now, you resolve it. E4 will come here. When you resolve it here, you are opening 30. So E4, which will be 2.16 times 10 to the power 7. Now you are opening, that will be sine 30. But you have to check, will it be positive or negative? By the time it comes here, it has to be radially inward, because the negative charge, so it's also negative again. Inward in this direction, the direction of inward here will be negative y. So it will be minus this, minus this, minus this. And you get your summation of E sub y. And that will be it for this video. Then you can now find your resultant that way. Do well to subscribe to the channel. Comment in this comment section below any topic you want me to cover that you don't understand in physics, college physics. God bless you. Please subscribe to the channel.